last time we looked at one formula for implicit differentiation where we had z as a function of two variables x and y, and we got this, what the book calls equation 6. And then we had skipped the next part so we could get to a problem where we applied that equation. But now we're going to look at another form of implicit differentiation where we have an equation in 3 variables, x, y, and z, and we'll assume that the z is a function of the x and y. And so it says then we can use the chain rule for a function of more than 2 variables to differentiate both sides with respect to x, and we get the following. Okay, so we'll think of this whole thing as our w. And so we can take, since we have 2 independent variables, x and y, there are going to be 2 partial derivatives. There's going to be the partial of z with respect to x and the partial of z with respect to y. We're going to just do the partial of z with respect to x. The partial of z with respect to y would follow the same steps. Okay, so the chain rule says if we want to find w sub z, w sub x, sorry. Then we'll do the partial with respect to x. Yeah, there's a function of 3 variables, yeah. So we'll do the partial of w, or the function they call f. I think the book is always going to use the f in their formula, so I'll use f with respect to x, and then times the partial of x with respect to x, plus, and then we'll move on to y. So the partial of f with respect to y times the partial of y with respect to x, and then plus the partial of f with respect to z times the partial of z with respect to x. And then the derivative of the other side is just 0. Since the other side is 0, its derivative is also 0. But now we want to simplify each of these terms. We don't know what the function is, so partial of f with respect to x, there's nothing else we can do with that. We're just going to leave that as the partial of f with respect to x. Whoops, sorry. What about the partial of x with respect to x? That's 1, right? So since this is just 1, then we're going to have the partial of f with respect to x. And for the partial of f with respect to y, again, we don't know what the function f is, so we'll just have to leave that, the partial of f with respect to y. Now, what's the partial of y with respect to x? This one's kind of tricky. So let's think back to like this equation. If we were taking the derivative of both sides with respect to x, what's the derivative of this term? 0, right? If x and y are both independent variables, then we just treat y as a constant. So this would be the derivative of a constant with respect to x. So this part is 0, so we lose that whole middle term. Okay, and then we'll have the partial of f with respect to z. And remember, z is understood to be a function of x and y. So we'll still have times the partial of z with respect to x. And so they want us to solve for the partial of z with respect to x. So the first thing we'll do is subtract the partial of f with respect to x from both sides. And then divide both sides by the partial of f with respect to z. The book calls this, and then the corresponding equation for the partial of z with respect to y, that calls those equations 7 And the only difference, if we were doing it with respect to y, is the x's would change to y's. So I think then the next problem will probably have us apply this equation. 34, yes. So the first thing, though, that we have to do is we have to get everything on one side. Whoops. We have to get it set equal to 0. So we're going to subtract the natural log from both sides. You could also subtract yz from both sides. It doesn't matter.
Can I ask a really quick question?
Yes, of course.
For the one we just did, if we were doing like W of Z, would that change what term becomes 0 and what term becomes 1? Do you know what I mean?
Yes, but we would never take the partial with respect to z because z is the dependent variable. We'll only take partials with respect to independent variables. So if we had like g of x, y, z, w, then we would treat x, y, and z as independent variables, and then we'd think of w as a function of those three. And then we'd have three partials, and we'd get a similar sort of thing, yes. Yep. Okay, so in 34, you can, however you want to do it, get everything on one side. So I'm going to subtract the natural log of x plus z. And then, so I want to find f sub x, and then f sub z. Well, actually, we need all three of them. F sub x, f sub y, f sub z. This whole thing is our f of x, y, z. But remember here, never mind. So what is the derivative of the first term if we're taking the derivative with respect to x? 0 minus, and then 1 over x plus z, and then it'd be times 1. So f sub x is just negative 1 over x plus z. And then f sub y, the derivative of the first term will be z minus 0. So f sub y is just z. And then f sub z, so the derivative of the first term with respect to z is y, and then minus 1 over x plus z, and then just times 1. So the partial of z with respect to x is the negative f sub x over f sub z. So negative f sub x, then that will change this to positive, over y minus 1 over x plus z. Normally we would not leave a fraction within a fraction, so we could just multiply top and bottom by x plus z. So in the numerator, the x plus z's would cancel, and we'll just get 1. And in the denominator, we'd have y times x plus z, and you can write it like that, or you can distribute the y. I'll distribute. So I'd have xy plus yz, and then in the last term, the x plus z, so it cancels, so minus 1. And then the partial of z with respect to y. So it's negative f sub y, so negative z, over f sub z. So y minus 1 over x plus z. And again, I would get rid of the fraction within a fraction. So if I distribute it, I'd get negative xz minus z squared. And then in the denominator, we'd have xy plus yz. And then minus 1 again, so the denominator is the same. Okay. So 38 says the radius of a right circular cone is increasing at a rate of 1.8 inches per second, while its height is decreasing at a rate of 2.5 inches per second. At what rate is the volume of the cone changing when the radius is 120 inches and when its height and the height is 140? So they talk about volume, and volume of a cone, I think it's 1/3 pi r squared h. But on the back, let's go through, so this will be a good little Calc 1 refresher, how to get that using volumes of revolution. So how to figure it out is think of having a line giving, like if you had the cross section of that cone, focus on just the right edge. Okay, and so if we revolve this line around the y-axis, then we'll get a cone shape. And the radius of the cone is the radius of the circular portion at the top. And the height is just from its like apex to the top. So using that idea, what would this point be? What would the x-coordinate be? I'm not looking for a number here. R, right? And what would the y-coordinate be? H. And so we want to revolve that around the y-axis to generate a solid. And then we want to find the volume of that solid. And there were two methods that would be applicable here, the disk method or the shell method. And the disk method is the method I would use here. So the disk method is you take cross sections perpendicular to the axis of revolution. And so I like to draw in a typical cross section. So we're going to get a disk right there. And then I like to label just a representative point on the edge, and I'll just call it AB for now. It's obviously not RH here. The x's go from 0 to r, the y's go from 0 to h. This is some intermediate point. And so to find the volume of revolution, we have to integrate the cross-sectional area. So I want to find the area of a cross-section. In terms of, and then we have to decide, do we want the cross-section in terms of x or in terms of y? And looking at our picture, that should help us decide what variable we're going to want to integrate with respect to. Can you tell from the picture what variable are we going to integrate with respect to x or y? Yeah, this is it. If your instructor taught it differently than this, you might not be as familiar with it. But you want to look at how your cross sections are sliding. Are they sliding through y values, or are they sliding through x values? And so when I look at my cross section, when it goes from here to here, that's sliding like along the y-axis. So since it's like a vertical movement, then we would integrate with respect to y. Well, the area of a disk So one of these typical cross-sectional discs is going to be pi times the radius of that disc squared. Now for now, just in terms of A and B, which of those points represents, or which of those values represents the radius? The A, right? Because the radius goes from here to here. That's a horizontal distance, so that's measured by the x coordinate. So the radius is equal to A, which is the x coordinate, but we want everything in terms of y. So we're going to have to come up with an equation that relates x and y, and then we'll solve it for x in terms of y. Well, this right edge of the cone is just a straight line, so we can put it in y equals mx plus b form. What's the b? Oops, sorry. 0, right? B stands for the y-intercept, and I've drawn the line so it crosses at the y-axis. So this is 0. And what's the slope? H over r, because we go up h and over r, right? So now we can use this equation to solve for x. So x is, and we're just going to multiply both sides by r over h. So if the radius is equal to the x coordinate, this is the x coordinate in terms of y. So now we can use that the radius is equal to r over h times y. So then the area of a cross section is A equals pi times r over hy quantity squared. Or A equals pi r squared over h squared times y squared. Once you have the cross-sectional area, that's what you integrate to find the volume. So the volume is the integral of the cross-sectional area, so pi r squared over h squared y squared dy, and now we have to say what our limits are. So y is going from where to where? 0 to h. Now this r and h, those are constants because we're integrating with respect to y. So we can actually think of pulling that whole thing out in front of the integral. So that would just stay out in front, pi r squared over h squared, and then the antiderivative of y squared is 1/3 y cubed. So we have pi r squared over h squared times 1/3 h cubed minus 0. And so we have the 1/3 pi r squared, and then this h squared will get rid of 2 of the h's there, and so we have 1 h left. And I think that's what I said. I think I said pi over 3 r squared h. I can't remember. 1/3 pi r squared h, yes. So we're thinking of volume as a function of r and h. Okay. So we want to find the rate of change of the volume. So now what's sort of implied in here, and we don't really address it directly, is r and h are functions of what? Of what? Time, right? Because when they say increasing at a rate of 1.8 inches per second, then the radius is changing with time, and so is the height. So we know that r is a function of time, and h is a function of time. So this is like a case 1 of the chain rule, where we have the volume as a function of 2 variables, r and h, but each of those variables is a function of a single parameter, t. So this would be case 1 of the chain rule. And so we actually use dv dt, since there's only one underlying parameter. And then it would be the part, and I'm just going to think of this as, I'm not going to use f, I'm just going to use v. So it'd be the partial of v with respect to r. You could write an f there too, that's fine. And then times dr dt. Plus, and then the partial of v with respect to h, and then times dh dt. We're asked to find the rate of change of volume. So dv dt is what we're trying to find. So the partial of v with respect to r. So what are we going to get there? Right, 2/3 pi r h. And then dr dt, well, we don't know what it is as an expression in time, but they tell us the radius is increasing at a rate of 1.8 inches per second. So what am I going to put here then? 1.8, right? And then the partial of v with respect to h, 1/3 pi r squared. And then what am I going to put in place of dh dt? 2.5? Negative 2.5, since it's decreasing. And then the other things we can put in are 120 will go in for r, and 140 will go in for h, and then we'll have the numerical answer. So we have 2/3 pi, and then the r is 120, and the h is 140, plus 1/3 pi 120 squared times negative 2.5. So just, let's see, so I don't have to worry about using so many parentheses in my calculator, I'm going to factor out a pi over 3 and a 120. So let's see, 3 would actually, well, I'll do it when I type it in. Pi over 3, 120. And then what would be left would be a 2 times a 140 times a 1.8. One of the 120s is gone. I'm left with still a 120 and negative 2.5. So minus 120 times 2.5. 3 goes into 120 40 times. So I'd have 40 pi. And then 280 times 1.8 minus 120 times 2.5. So approximately 25635. What would be the units on that? It's something per second. It's volume, inches cubed, right?